到时候你去给我拍照，我还以为你说话，我以为你会下一句就说那个方便面，超级好吃，有方便面，就那种海南的，是那个香港的，是一个便宜，但是我到时候可以直接找到。然后他们上面是汉语面是，
没发现他们一边吃一边喝。
然后把它下在那，
你想想得多丑。
然后我跟他说，我跟你讲，对呀，方便面手指。我妈都不去逛外面的东西，你就楼下这两发烧的。你有关系？你这么说。
你们还澡堂吗？那就是可闷了。跟他们签订打。
So very good evening. So how are you today? Perfect before semester break. So next week is no, tomorrow is the Labor Day, right? Yeah. So some of you might enjoy your holidays. No. I think tomorrow is a public holiday.
Yeah.
So no class tomorrow.
Yeah.
So maybe you have something like the recorded lecture if you have any classes for tomorrow, right? Yeah. So by the way, a few hours before we celebrate our Labor Day, so today we're going to discuss about this lecture 7, right? So today we just discussed about the cross dependency that we touched a bit last week, and we're going to introduce you some tests for the autocorrelation and also integral scarcity. And we'll move towards to test for the stationarity. So that's the main topic we want to cover for today's lecture. So what we concern about what we say is Hanner unit test. So then next week we're going to next 2 weeks, right, after semester break, then we're going because as we know, each country or each firm going to have their characteristic, right? So their residual, especially when we estimate in the panel setting, their residual might correlate with each other. If this what we say cross dependency happen, so it will make our test become invalid, right? So for example, the test like the variables actually is significant, but impedance become insignificant due to this cross section dependence. So we have to take into account this issue. So today we will focus on two parts. One is the model selection, which focus on diagnostic test. Then we will move towards to the panel engineering test. So that's the thing we're going to discuss today. So we will use back the investment models that we used in the previous lecture. We are going to focus on the two independent variables as usual. So we will go to focus on the BAL and also the CAP on the investment. That's the thing. Okay, so yeah. So we were going to discuss on these panels, what we say is panel cross dependency test. So we are going to have 4 different tests. So 4 different tests discussed in the literature to test for the cross section dependence. Actually, for example, I have a 10 firms, right? For my investment models. So is there really a cross section dependence? If there is no cross section dependence in our data set, then after we use this test to test it and then found out that actually there is no issue of this cross section dependence, then we don't need to care about that. We don't need to care about that. So we just proceed with the approach that no need to take into account this cross sectional dependence. Okay. So that is what means by this the purpose of the test here. So okay, so what is the issue here? So the issue here, right, because we assume this discipline refer to the residual. We assume the residual in the panel model are cross-sectional independent, means that independent, so they are not affecting each other. In fact, actually due to certain reason, right, they're affecting each other, maybe because of their characteristics, etc. So we are going to test it out. So it's common if we assume these are cross-sectional independence. So we just proceed with the conventional unit test. We just proceed with the conventional approach. So what is going to happen, right? So we want to prove that whether is there any cross dependency or not. So when our sample is large, right? When our what we say the cross-sectional dimension is large, if we involve a lot of firms, for example, in our example we only have 10 firms. Let's say we have 50 firms, 50 firms. So do you expect some cross-sectional dependence? Yeah, right. I'm sure, yes. Then, for example, like only 5 firms, maybe not, because they may have a minimum something like the cross-sectional dependence, cross-sectional individual for us to proceed with the panel. Conventional one like above 5. I don't think if you have a 3 firms or 3 countries, that is, you have a reason to proceed with the panel, right? Because only 3, that is very difficult for us to justify why you want to proceed with the panel approach. So minimum 5, as I noticed from the previous research, minimum 5 there, and that with this limitation in the time, so they will proceed with the what we say this panel approach. So normally this cross-sectional dependence, it will become serious, right? When we have the huge N, so because it's notably, right, it's a considerable evidence that cross-sectional dependence is present in this when we involve with a very huge N here. Huge N means that many firms, many countries, a lot of countries, a lot of firms. So it means that a big N, right? So if you ignore what happens? If you ignore this cross-sectional dependence, what will happen? If you not take into account this what we said cross-sectional dependence, you will make your estimator become not efficient. You will lose your efficiency and also make your test statistic become invalid. So this is our concern here. So how many tests? yeah, a lot of tests, a lot of the what we say diagnostic tests for urge to test for cross-sectional dependence. So if you we have 4 tests, at least we have 4 tests here. So what are the difference here? Actually, as you observe from the years, right, start from 1980, already proposed by Bush-Buchan, Lagrange multiplier. Then the Pasaran came in 2004. He proposed this what we say skill LM test. We also have the Baghdadi. So actually, it's the aims to correct some certain issue from the original one. Then they proposed to this skill LM test, and then bias corrected skill LM test. Then we also have this Pasaran 2004, which we call as a cross dependency test. So this is widely used in the research as compared to the Baghdadi et al. 2012, because this Baghdadi 2012 et al. 2012 is just corrected based on the original skill LM test. So it does not take into account the issue which proposed means that which raised by this 2004. So let's see any difference here. So before we proceed with the diagnostic test, right, and to understand the hypothesis. What is the hypothesis here? Actually, the hypothesis is testing whether there is a correlation, right, among this residue. So as a H now equals to 0. So we assume no cross-sectional dependence in the residue as a H now. So we are testing this hypothesis. There is no cross-sectional dependence in the residue. So this is our H now. We also can rewrite it as a correlation for the residue is equals to 0. And I is not equals to the J. 9 not equal to the J. This is our hypothesis. So how to test this what we say the correlation, right? So actually we have to form this what we say this first. What is this P for? Actually this is not P. See, a bit smaller. So what is this P stand for? It's a product movement correlation coefficient of the residue. So as you observe the P, what we say the rule, right? The rule here appear in all the test statistics. So it's actually referred to product movement correlation coefficient of the residue. So they compute the residue. They compute after they compute the residue, then they calculate it, right? They calculate residue with the residue and residue power of 2. Means this residue sum of square, right? Amongst the firms, it means that across the firm at time, then they calculate, then they get the rule here. They get the rule. Once they get the rule, then they try to form their test statistic. So based on this Bush-Buchan, right? In 1980, for this Lagrange multiplier test, actually, what's the limitation here? What's the limitation? As raised up by this skill, right? So skill actually is not appropriate for the to test when we have a large N setting. So this original test in 1980 is not suitable. It's not suitable when we involve a huge N. It means that you have many firms, many countries. Actually, this diagnostic test may be biased, right? I mean this what we say the Lagrange this Bush-Buchan Lagrange multiplier test may be biased. So this formula for test statistic proposed by Lagrange multiplier proposed by Bush-Buchan. So that's why to account this shortcoming, right? That's why this Pasaran they come up with the called as a skill Lagrange multiplier test. So in a short form they put Lagrange multiplier subscript S. So in order to account for what? To allow the test to involve with the it means that to be not biased, to be unbiased for the large N. To be unbiased for the large N setting. So you can see in the original test, the chi-square distribution is for the N fixed. For the T is infinity. But under this skill LM test, which proposed by Pasaran, is for the T go to infinity, like the Bush-Buchan LM test, means that as well as the N go for infinity. So this is one of the advantage as compared to the original test in 1980, right? But in the literature say what? In the literature say this test statistic, even though already accommodate this limited N issue, right? But this statistic also got a size distortion if we have the small t. So even though it's account the limitation in the Bush Pagan in 1980, for the limited n, right? If you have a, means that this test was suitable for the large n. Then you come up with the scale one, right? But this test will be distorted also when we have the small t. So then, even though here say t go to infinity, right? But already got research proof that this test is going to have a size distortion when we have a small t. And this distortion going to become more serious if we have a large n. Even though you solve the large n issue, but how do you solve the t issue, right? Even though you say you have a very huge t, then but you're going to have a problem when you have a small t. So the Pasaran 2004 come in. The Pasaran 2004 come in to solve this issue for the original Lagrange multiplier and also for this scale Lagrange multiplier. This Pasaran proposed another test. They use the average of the pairwise correlation coefficient instead of the original value. They just make some adjustment. They use the average. They use the average and then form another test statistic. So instead of based on the original original pairwise correlation coefficient, they use the mean. They use the average of this pairwise correlation coefficient. They use the average instead of the original. So this test is likely to have a good properties for even though you have a small n and also small t. So this test is coming out to solve the issue in the original Ln and also the scale Ln. So you can see the chronology, right? The original test, and the scale version, and also the Pasaran version. So another version is proposed by this Baltaki et al. Actually, this one is a bias corrected because you already mentioned that, right? This scale Ln test got issue, right? So this Baltaki in 2012, they offer the test to means that a symptomatic bias corrected for this scale Ln test to solve the issue that highlighted in this scale test. Because you say talking about the small t, right? So how to solve the small t in this Pasaran scale Ln test? So this Baltaki et al. They make some adjustment. So we said that this test, we propose this asymptotic bias term. They propose this asymptotic bias term, which is n over the 2 times t minus 1. So we use this the bias term to solve the small t issue in the scale Ln test. So to make the residual to be something like much more precise and then calculate the Lagrange multiplier statistic. That's why this is called another version. So you can see the chronology, right? The chronology, and also nowadays also got people trying to extend the Pasaran 2004 statistic, right? Still a lot. So now let us try to apply. Let us see whether we have a cross-sectional dependence, right? In our estimation or not. So you can estimate your models. You first estimate your model first, right? Estimate your models, and then can you still recall how to estimate your model? The investment models. So you have investment, VAL, CIP for the 10 firms. So what is investment already? IMD stand for investment, right? And then VAL stand for market value of stock. CIP stand for capital stock. So for this 10 firm, and then this residual here refer to the epsilon here refer to the residual. So you have to estimate in the fixed effect specification. Then you see your diagnostic for your residual. So okay, so now you can go to your last week lecture, right? You can use your last week lecture. Yeah, you can use your Quanfield part 2 lah. Quanfield part 2. Quanfield part 2 here. That's the part 2. field part 2. So you can estimate them in a fixed effect. So you can go to equate, you can go to estimate equation, go to equate, go to estimate equation, then type your equation, right? Investment first, INV, then C, right, constant, then CAP, VAL, right? CAP, VAL for the 10 first. Then panel, cross section, right, is a fixed effect. Try to put their estimate as a fixed effect. Then you click OK. So again, now you go to equate, estimate equation, type your equation, right? INV, constant, CAP, VAL. So once you type this, go to panel option, then cross sectional here you put fix, right? You put fix, then you click OK. Then now it's time for us to test, right? Because I want to see whether this the residue in this 10 are they affect each other's, right? Are they got a correlation or not? So I go to view, I go to diagnostic for the residue diagnostic. Do you see this cross-section dependency test? Cross-section dependence test, you click on it, yeah, this is the result. So after you estimate, right? After you estimate, you click OK. Then it's time for us to diagnose this model. I want to see whether there is a cross dependence or not, because my hypothesis, where's my hypothesis already? I'm estimating this model, right? I got my dependent variable, right? This is my dependent variable, and then I got VAL, CAP. So now I want to check this residue. So you mean this one actually want to see the correlation for the IT and also the correlation for the JT. Are they equals to 0 or not, right? Correlation. So this is my hypothesis, right? This is my hypothesis. So I want to check whether there is no cross-section dependence in the residue, or there is no correlation in the residue among these 10 firms. So I want to diagnose this residue. I want to check. I want to use the 4 different tests which we mentioned just now, including the Bush, Bagan, test 1980, and then the skill version, as well as the Persara 2004 version, as well as the Baldagi et al. 2012 version. So we have 4 different tests to see whether am I have evidence to reject the hypothesis or not. Okay? So I go to eView here, I go to view, then I go to diagnostic for the residue, then I check for the cross-section dependency test. So this is my result, right? So we have the original Bush-Bangtan LM test, which has been predicted have a limitation in the when you have a large n, right? Then we also have the skill Pasaran version, which also has been predicted your test will be biased. Your test statistic will be biased when we have a large t. This test has been predicted when you have a large n, and this test try to solve the Pasaran Bush and Bangtan, but have been predicted when you have a large t, right? Then after that, this one try to correct the skill version. So this is a test statistic which proposed by Baldagi et al. 2012, and this is a Pasaran cross dependency test. So as you observe, that test statistic is different, right? Because this one they use an average version of the what we say the rule, right? Average of the rule instead of the actual value. And these three are the test statistics we mentioned just now. So now with the degree of freedom 45, so these are the p-value for each statistic. These are the p-value for each statistic. So if we based on the alpha 0.05, for example, 5%, so all the p-value here actually is lesser than 0.05, right? So they are significant at 5%, right? They are significant at 5%. So if significant at 5%, what it means? So it means that if it's significant at 5%, so you reject the hypothesis, right? You reject the rationale already. So once you reject the rationale, so it implies that there is a cross-section dependence in the residue for our estimation. So there is evidence of the cross-sectional dependence in the residue. So given us all the significant p-value, so we have evidence to reject the hypothesis. Very significant, right? So we have evidence to reject the hypothesis. So we can say that actually there is a cross-sectional dependence in the residue. So I also do some elaboration, right, in the files. So we say the value of the test statistic is one by one now. It's fell into the upper tier of the chi-square 45. It's follow the chi-square distribution, because you see all the test statistic is follow the chi-square distribution, right? Follow the chi-square one. Follow the chi-square distribution for all the means for all this statistic, right? For this statistic. So we reject the null of no correlation at the conventional significant level. So if in the final exam, right, if it not give you any significant level, so you can either use 0.05 or 0.01. So it's up to you, okay? So for conventional one, I will use 0.05, okay? For this alpha value 0.05. So if you then we also can see that for the skill version and also the Baldagi version. So this one is a standard normal, and so also reject the null at the conventional level. Then how about so we can see these two, right? 21.4, 31.14, right? The test statistic almost same, right? So actually the bias correction proposed by Baldagi actually have a small effect, have a small effect on the skill version. And so we want to see, actually we can see normally people will look at the Pasaran CD test, the last line. That's why you can see the journal article I shared. They also show this means that the Pasaran cross dependency test instead of the original like the Bush-Bangtan LM test, because they know their limitation, right? So it's significant below the skill LM test, so you still reject the null. You still need to reject the null. If the question asks you to explain the test statistic, right? So you can say the p-value is significant for all the 4 tests. So you reject hypothesis, so we can conclude that actually there is a cross dependency in the residue. So it means what? It means that whatever we estimate in the previous lecture, actually the test statistic is invalid. It's not that accurate, right? Not that accurate. If you raise out the issue cross-sectional dependence, then your estimation in your previous lecture actually is not that accurate anymore, right? But as you observe from the journal articles, right, once they bring out the issue cross-dependency, normally they try to use an approach that solves the cross-dependency. For example, they use the Sher estimation, etc. to solve, instead of based on the conventional like fixed effect, random effect, to just based on the pattern approach. So if they bring out the issue cross-dependency, normally they will use the approach to solve the issue. That is the something like design, right, for your research for your papers. If they don't want to bring out the cross-dependency, they just want to see the determinants for the investment. So they just bring out the issue, use the Hausman test, use the Bush-Crosby test, right? Bush-Quantum test to determine between the fixed or OLS, random OLS, and then go to the Hausman test. Then they do not touch on this cross-dependency. If they touch on cross-dependency, if there is insignificant, then they are safe, right? Because their estimation is still valid. But like our case here is significant. Then how? Significance means that whatever I estimate in the previous lecture actually is the result actually is affected by this cross-dependency already, right? So we have been quotient. Then we have to use the estimation, for example, the Sher similarly unrelated regression to solve this issue cross-dependency. That is practice in this research. So that's the things about this cross-dependency. Then how about this heteroscarcity? So because of this, as I mentioned just now, different country have different characteristic, right? So in order for us to test this heteroscarcity, even though researcher much more concerned on this cross-dependency rather than the heteroscarcity, but we still can test for it to see whether the residual are homoscarcity or not. Because in a time series, we also test for autocorrelation, right? Test for autocorrelation, test for heteroscarcity, to test for non-normality, right? So panel also allow us to test to see whether the residual, whether the variance for the residual are constant or not. So this actually is a diagnostic check to see the variance for the residual constant or not constant. So if the residual not constant, what it means? If the residual not constant, it means that our standard error is no longer efficient, right? No longer efficient. So that is the issue of this heteroscarcity. So eventually it will affect our estimation for the test statistic, for the what else here? The interval estimations, right? So that is the issue with this if the assumption, if this hypothesis is rejected. So how we're going to test it? So if you go to the view here, right? If you go to the view here, that is the diagnostic for the residual, right? So if you can observe here, there are 4 different buttons, right? One is histogram. We also can test for whether the residual is it well behaved or not? Is it followed normal distribution or not? Normally monitored because this maybe our result affected by the outliers, or maybe like the GM, right? Like one of the firms actually is maybe it's a giant, so actually we have outlier issues. Outlier means that the one firm actually behave totally differently from the rest. So actually we cannot put them together. There's outliers in the panel settings. Outlier. For example, if you remove out this the outliers, right, you will make your result become normal. Will become go back to much more accurate without the outliers. So that is we can use this histogram to check whether there is an outlier issue. Then this one arena unborn actually is for this what we say is for the GMM method, right? So now go to this heteroscarcity. You go to the heteroscarcity. Period GRS. No method, right? Let me see whether I put none here to see whether. Okay, go to view and then go to diagnostic for the residual. Check on heteroscarcity. Okay, so let me see. So the result shows here, right? The result here. So what it means? It means that my result, right, follow the 10 degree of freedom actually significant. So it's actually reject my hypothesis. So residual actually is heteroscarcity, right? The variance for the residual no longer constant. So no longer constant in our estimation for this 10 terms. Because the rationale is residual are homoscarcity, so we reject the hypothesis because it's given us the significance of the p-value. Because this p-value is 0.000, right? So it's lesser than this 0.05. So we reject the hypothesis, so we can conclude that the residual actually are not homoscarcity, So the residual actually is a heteroscarcity. The variance for the residual are not constant anymore, right? Are not constant anymore. We also have a panel period, right? Also similar panel period. We have the there's another test, right? To test for the panel period. Also significant. The result also shows that the residual are variance for residual are not constant. So okay, so that is the heteroscarcity test. So what else we can diagnose, right? So can I use this residual plot, right? I can plot the residual actually. I can replicate this residual. How to plot it? How to plot the residual, right? You can go to view. Yeah, you can go to view and then you can go to residual graph also can. You can put the actual with the residual graph or residual graph. If you click on the residual graph, then you can observe the graph here, right? So you go to view after you estimate, you go to view just now, then you go to the actual fitted residual. You click on the residual graph. Once you click on the residual graph, you can observe that how come the residual is a difference between your estimated and your actual investment, right? So that's our residual. So you can see the residual for the firm 1. This 1 refer to the firm 1, 2 refer for the firm 2, 3 refer for the firm 3, right? And also up to the firm 10. How come the residual from the firm 1, 2 and 3, maybe 3, right? Up to 3 here. This one is for 3. Firm 2, firm 2, right? Firm 2. How come the residual from the firm 1 and firm 2, maybe firm 3 here? How come they're totally different with the rest, right? With the rest. Is it something happened here, right? Am I right? So that is one of the symptoms for us to see how come firm 1 and firm 2, the deviation, estimated value from the original value, how come deviate a lot, right? Compared to the rest of the firm. The other firm, okay. How come here deviate a lot? You see? Deviate a lot, right? As compared, it's outside the boundary already. So that is one of the symptoms for us to say, oh, there is something happened, right? In my estimation here. When you so actually it's just a little bit abnormal, right? Abnormal because if you just based on the residual, it's a little bit not that formal. It's not that formal because in order for you to because it's a little bit difficult also, right, for us to say, oh, firm 1, firm 2, right? Is it means that I need to remove the firm 1 or remove the firm 2 or remove firm 1 and firm 2, right? So a little bit difficult, and also the justification also quite hard, right? Is it why I want to remove the firm 1? Why I want to remove the firm 1 and firm 2? Is it because really deviate a lot from the rest? So is it because my estimation issue? Is it because I ignore the cross dependency? That's why I make my residual plot different a bit. So that is an issue you can take into account, right? So actually you can have a much more formal test, to identify the outlier. You can see the paper by Liu, right? 2015. By 2015, this Liu got mentioned that actually he got used this test to identify the outlier. We also have a much more formal test like defeat in the panel. You can try to take a look at defeat. It's called defeat, D-I-F-F-I-T. If not mistaken, I spell it correct. defeat also can use in the panel to look for outlier in the panel setting. Right? So I think I heard this one from the 2015 because he said that, is it really a problem or not? Is it the outlier really an issue? Yes, he said outlier can result bias in the parameter estimate, right? So you have to detect the outlier. So this rule 2015, they use the use the approach to get to detect the outliers. So that is you can take a look at the original paper by this group. I think I show you this one, outlier pattern. Right. So you based on this various reminder disturbance. So I don't think, because it is much more on statistic, right? Much more on statistic to account for the outlier, because outlier got so many different types. Is it this one is what we say is it the outliers, or is it the inferential point that normally raised in the statistic? So actually, in order for you to detect it, so normally people will use this what we call the robust statistic, the robust approach to accommodate this outlier. Instead of you remove them. So that is a discussion in the statistic. When we have the outliers, some suggest that remove the outliers. Some suggest that we have to accommodate the outliers. Right? So there are two different schools of thought. Either you want to accommodate them or want to remove them. Accommodate them, you have to learn, right? For example, like this robust statistic in the panel setting to accommodate the outliers. Or else, you use the statistic to detect the outlier, then you remove the outliers. So there are two different schools of thought, right? So you can go through the paper to take a look how the researcher they try to detect the outliers, right? They also plot the residual against the fitted value, right? And then to use the LM statistic and then to see which one is the outliers. So deduce the things. Okay. Okay. So now that is the means that the panel approach combined with what we discussed in the previous lecture on this fixed effect, right? We start with the POS, fixed effect, random effect. Then we introduce you the hypothesis test, right, to choose amongst the models. Then to that lecture, we also introduce you the diagnostic check, means that to see whether there's a cross dependency or not, and also some heteroscedasticity test, and then introduce you the normality plot also, right? So I'm a normality plot, so you can actually go to the view here, then you can go to this diagnostic for the residual. You can click on the histogram for this normality plot. Yeah. So this normality plot actually proposed by the Jacques Bera to see the residual whether follow the normal distribution or not. Is based on the skewness and kurtosis. So skewness have to near to 0, kurtosis near to 3 in order for the residual to be normal distribution, right? So based on this Jacques Bera statistic, what we can observe here. So maybe I make it bigger in this one, right? This is a normality plot. So based on this skewness have to near to 0, right? Kurtosis near to 3, but it's far right of kurtosis, right? So that's why our Jacques Bera statistic, this Jacques Bera statistic is proposed by Jacques Bera. So the statistic is follow the chi-square distribution with the degree of freedoms 1 or 2, I think, 5 or something, right? 5%. So the p-value here is significant. The p-value here is significant. So you reject that. So the reject the hypothesis. So we can say that. So what is the hypothesis here for this Jacques Bera? Is a residual follow the normal distribution. So against alternative Hirschsprung not true, right? So this is the normality test actually. So this is one type of the normality test. It's proposed by Jack and Vera. So the hypothesis is residual follows the normal distribution. Again, alternative, the residual do not follow the normal distribution. So the p-value here is lesser than 0.05. So significant, right? So you reject the hypothesis. So our reject the rationale. So the residual actually do not follow the normal distribution. So that's why you also can observe, you can also complement the result with your residual plot just now, right? Especially for the Fermat two also debate a lot compared to the rest. So no wonder the residual does not follow the normal distribution, right? So that is what we can conclude from the graph here. What else? Nothing else. So okay, so that is the diagnostic test, normality, control scarcity. We also have this cross dependency for the panel setting. So now it's time for us to move to the second part on this panel unit test. So for this panel unit test, right? Actually, in our time series, before we move to the co-integration and also univariate uniroot, still remember the univariate uniroot we talked about the ADF, augmented Dickey-Fuller, right? KBSS, unpaired. So actually, why we want to proceed to the panel, right? Because of the short sample, right? Short t, and then do not have enough observation, and then we want to have a more degree of freedom, more flexibility, so we extend to the panel. That's why in the panel, we also have this panel, what we say, this spurious regression issue, right? Like, but we do not account it, right? When we estimate the investment function before the lecture, right? We just estimate it. So let's say if my investment is I naught, then my another two independent variable is I1. Can I estimate such a regression without accumulate anything? Cannot, right? Because if our estimation make sure of I1, I0, like what we discussed in the previous lecture in the time series. So we also have the problem of the spurious regression, right? So we have to take into account this spurious regression. No matter in the time series, we also have to take into account in the panel. So that's why we have to. It's much more challenging for us, right? Because not only we have to take into account the cross dependency, right? We also have to take into account the spurious regression as we have done in the time series. So now, because a little bit challenge because we compare the result for the cross section, right? You can imagine, right? We not only want to take into account the what we say the cross sectional issue, right? Cross dependency issue. We also have to take into account the what we say the spurious regression, right? So because we have many and also have this I1 issue, spurious regression issue. So today we're going to just focus on the first generation panel uniroot. So after the semester break, we're going to focus on the second generation panel uniroot. So any different first generation, second generation, just like the four cross dependency tests just now. We have the conventional one. We also have the improved version, right? Like the Bush-Vagan test is the original one, right? Then we have the Pasaran cross dependency test in 2004. So it's also applied to the first generation and second generation. The first generation that assume cross-sectional independence. The topic we're going to cover after semester break, second generation, which assume which cannot assume if we test the series, right? Actually, there's a cross dependency. Then we have to use the second generation panel uniroot because that panel uniroot test is purposely used for if our data set has the cross dependence. That's for the second. We have to use the second generation panel uniroot test. Okay, so that is just a summary for our first generation and second generation. So okay, so the first generation, right, just involve testing on the pool data, on the pool. So just like the time series, we also have to take into account the model, whether we include the train or or include the intercept, and then how many leg length, right? So we also have to use this model selection criteria to help us to select the leg length. Okay. So now, remember this first generation is cross-sectional independence. It's assumed that, it just assume, that's why second generation come in. So it's assuming cross-sectional independence. So there is a drawback with this, what we say, this conventional panel unit. So, so why we don't want to use the conventional one? What we said, the univariate. Go back to the univariate. What is univariate? Univariate is like the time series. Because you have, for example, you have 10 terms, right? Can I ask you to estimate individual investment? It means that, can I ask you to estimate, can you tell me which firm investment is I naught? Investment series is I naught. Can you tell me that? Yes, can. You can run conventional unit test, right? For the firm 1, for firm 2 up to firm 10, right? Then you can see, oh, firm 1 is stationary, firm 2 is not stationary, firm 3 is stationary, firm 4 not stationary, right? So you have a mixed result. Maybe that, I just imagine, right? Maybe. Then I will ask you again, how about BAL? Can you tell me which firm BAL is stationary? Can you tell me? Can, right? Again, run the conventional unit again, right? Univariate again, firm 1 ADF, firm 2 ADF, firm 3 ADF, right? Etc. Then I ask you again, how about CFE? Oh, again, right? So how many set of ADF, PP, KPSS, parent for you to run for 10 firms? Wow, uncountable, right? Are you going to headache? Migraine already. Or disease. That's why the panel coming, right? The panel unit will help you to solve this problem instead of for you to run the univariate unit, right? Because univariate unit only for single country or single firms, single series. If you combine them together, actually you just estimate one only, the panel. In the panel setting, just come up with the panel, general conclusion for the investment, general conclusion for the CFP, and general conclusion for the BAL. Just general one. But this also is a limitation, right? Because you focus on general. In a full setting, that's why you assume that they are not affecting each other, right? So you just give a general, oh, I said investment is I1, CFP I1, BAL I1, right? For all the 10 firms, right? So that is what we want to do today.
So in this case, for you to apply panel group, you need to have multiple variables. So you cannot just use like for example, like housing prices. I have like different house types, and I have housing prices, but I have no predictors. Can I still do something with a panel group?
Yeah, can. You not necessarily is for estimation, right? You can see, for example, I want to see the house price. Is it stationary or not stationary? Just focus on one series. Can. I want
to combine all different house types, housing prices.
Different housing prices for different country.
Malaysia.
Or Malaysia. Why you have a different house price for Malaysia?
I want to estimate house prices based on the types in the upcoming future, but I don't have any predictors.
House price, is it only house price, for example, terrace?
Yes. So yeah. So semi-detached, detached.
Oh. House price. Can, I think can, right? Can. The house price, right? But house price you have a semi and then I think can, you can combine, right? From my understanding, for example, the stock price. Yeah, stock price. Yeah, I can stock price. I want to see the stock price in Asian 5. Are they stationary or not? So I combine the different country stock price, then I estimate. So for your case, house price, right? So you combine all the house price, then you estimate whether they are stationary or not stationary, right? I think same issue, same.
Because I'm doing by states as well, so I have a lot of ADF, KPSs. So imagine like 14 times 5 different house types for like 40 years. So there's a lot of big numbers.
you have to use the second generation already. Because you have so many, yeah, I think better use the second generation, right? Later, state. Not only you also have state. Then how you, then I think it's a state
Yeah.
for all the state, then the house price for the particular state. Right?
Okay.
Maybe it's maybe like that lah. Terrace for all the state, the house price for all the state, right? And then the bungalow for all the state. Then can combine lah. Then like that lah. You cannot combine the different house price. It's a different thing, right? It's a different, right?
Yeah, that's what, there is difference in price and
Yeah.
some others require.
Maybe for the bungalow, the house price for all the 14 states. So like that lah. I think should be like that lah, the setting. Okay, so now, so we need to improve the power, right? So in order to remove something like to improve the power of the unit road, sometimes because of the limitation in data, right? For example, like my case only have how many years? 20 years, right? 20 years. Then for you to run the univariate unit road, maybe you have a question about the time. So in order to improve the power, right, for the univariate unit road, so you can use the panel unit road, right? Panel unit road. So in its e-views, right, there are 5 different tests, which for the first generation. So under this first generation, they have 5 different what we say the panel unit road test. So which is called what we call maybe I call it full name now, Levin, Lin and Chu 2002, Breton 2000, Pasaran Shin 2003, Fisher Type MPP is proposed by Mandala and Wood 1999 and Choi 2001, Hadri. So these are the 5 different tests. But all these 5 different tests assume cross-sectional independence. Assume cross-sectional independence. So these are the characteristics. So that's why this is called first generation, right? It's a required cross-sectional independence. So we're going to discuss one by one, but we just give you the general idea, okay, what is this test about. So as we call, right, like what we discussed in the time series, so the AR, right, the AR process, for example, this one, because this is just a focus on the uni root, right, it's a series by series. For example, I have 3 different variables here, right, investment, CAP, VAL, so I'm testing them individually. So I want to check whether investment, stationary or not stationary. So this one is Y. Y here means refer to either is investment, CAP or VAL in my case, subscript IT. So I want to, for the rule here, is an AR term, right? So it's Y IT minus 1 is a lag. Lag for my dependent variables. And then with the others, what we say exogenous variables. Exogenous variables, for example, like intercept or trade, okay? So this one, how to test? If your current YT is exactly depends, means that depends on your previous Y. If your current Y is depends exactly by the previous Y, means 1, right? Then we say uniroot. It's a uniroot. It means that it's affecting your current Y affected by your previous Y. So it's means that okay, 1-to-1, right? 1-to-1 relationship. If the root is equals to 1, if the root is equals to 1, no matter it's positive 1 or negative 1, so we can say the Y actually contain a uniroot. They are not stationary, they are uniroot because it's completely affected by the previous Y. Then how about less than 1? If less than 1, then we can say that it's weakly stationary. Even though they have some uniroot, but it's weakly stationary. Right? So in order for you to test, you have to transform this model in this equation 1. So this is our test equation. So all the variables have to be in changes, right? So changes. Actually similar idea like we're testing the row equals to 1 or not equals to 1. So actually testing the significance of this alpha value, right? Significance of this alpha value that we discussed in the like the previous lecture, right? So we are testing this alpha value. So parameter. So what are the assumptions here? So persistent parameters are common across the cross section. So you can see the PI is equals to P for all the I, for for all the I. For example, the test for LLC, Breton, and Hardy. For these three tests, okay? These are the assumptions. So the PI equals to P for all the cross-section. So this our test equation is ADF specification. So okay. So what is the Hirschsprung? Again, similar like the conventional, like the univariate uniroot. Uniroot as a Hirschsprung. Uniroot as a Hirschsprung because we are testing this one significant or significant. If this one is not significant, right? So we feel to reject, then we say it's a uniroot. We feel to reject. So it's significant, then we reject it, right? We reject it, so it's no uniroot. We reject it means no uniroot. So if the test significant, so there is a stationary. If the test significant, there is stationary. But there is a different conclusion for the Hardy, like just like the KPSS. Because the KPSS Hirschsprung is no uniroot, right? Stationary, right? Hardy also said. Because this Hardy, just a story, like the Hardy, right? We look at the LLC and Breton, right? Oh, this LLC Breton or Hirschsprung is uniroot. So I want to improve the power of my test and want to avoid this over reject hypothesis, the Hirschsprung. So I come up with a test that contains the no uniroot as a Hirschsprung to get rid of this over reject the hypothesis. Means that to question about the power of the test. So he proposed another version. So it's called he named it as a Hardy. Use his name. So name it as a Hardy. So and then with the Hirschsprung no uniroot. So for this test, if you reject, means that your actually your no uniroot, right? You reject means your series actually uniroot. So it's the other way around. Something like KPSS here. So the other way. So you have to be cautious. Hardy test have a different Hirschsprung. Okay. So this is the LLC. So let's go one by one, right? LLC is proposed by Levin, Lin, and Chu. So we call it LLC. So it's a normal in the literature. They name it as an LLC. So you can see there's two different model here. So actually how it's come out for these two different models. One is the changes. The other one is the no changes. No changes. So after he estimate, right? After he estimate, then he want to remove the autocorrelation. Because in 2002, right, they were already aware of this autocorrelation issue, right? So he said, okay, after I estimate, I regress this equation and got this equation on my the lag, right, on their respective changes, right? So after I estimate, I remove the autocorrelation. So after I remove autocorrelation, I use these changes. It means that use this, and then I put it here as my dependent, and then use this after remove the autocorrelation as my independent variable. Then after that, I get I calculate my test statistic. So this is the idea behind the LLC. So after it means that after they just this is a test equation. Then after that they remove the autocorrelation and then they form their test statistic. So this is the test statistic. So this is the test statistic. Then actually you say the power of the test, right? Actually they complement each other. Just a different unit. Just like the augmented Dickey-Fuller, right? They complement with the PP, right? Because of this autocorrelation issue, so they come up with the augmented version, they come up with the PP version, right? And then because of the size of the power of the test, they come up with the KPSS version. So this one, actually, you can see the researcher, right? They report several panel unit to complement each other, to come up with the one conclusion, one final conclusion, whether the investment, for example, in my case, stationary or not stationary. Okay? So you can use your series, right, for the investment series. So you can go to the e-views here. So for example, I want to click on the investment. I want to see my investment series for all my 10 firms. Are they stationary or not stationary? So I go to view, then I go to unit test. I go to view, I go to unit test. So from this unit test, you can see there are two different here. One is cross-sectional independence, another one is a cross-sectional dependence. right? So this one we're going to discuss next week, right? This one is a little different, discuss next week. So cross-sectional independent. Once you click on it, they come up with this general box, right? So again, we go to view, Uniroot test, click on the cross-sectional independence. So here, test type, once you scroll down, there's a test we're going to discuss one by one. So the common root means the pi equals to p, just now, right? The common root. You see here we have a common root, which I mentioned is LLC and Brittle, right? Let's see. Is it LLC and Brittle? Yeah, LLC, Brittle, and Hartree. So the pi equals to p. This means by common root. So the pi is equals to the p. So it means with the common uniroot processor. Okay. So this is LLC. Then just like you test whether you want to test a level first difference, right? So normally I will test for level first. I want to see whether the investment series is stationary in level or not, right? Then what you want to put in your test equation? Is it intercept only? Or intercept and trade? Or none? Right? So in the research, right, normally we will report all, right? Normally people will report intercept and trade, right? Then you can see the journal articles they publish, they have a table summarized for all the results, model with the intercept, model with the intercept and trade, right? And then level was different for the series. So let's say this one, I just check in the individual intercept, and then for the lag length, because you want to decide, right, as you observe from the model, we have to decide how many lag length, right, here, right? Can you see? How many lag length here? How many lag length to solve for the autocorrelation, right? How many lag length? So how are you going to decide? Model selection criteria again, right? Model selection criteria, I click on the automatic selection. So when you scroll down here, there are a lot of model selection criteria like you did in the time series, right? So let's say, normally people will use AIC or SIC, right? So I use SIC for example, and let's see my example. I use modified, okay. Modified version, mean that adjust something, right, to accommodate some limitation. I use modified SIC, the Scotch information criteria. The maximum lag here that put star. You mean I don't put my maximum lag. I let because how the EViews determine the maximum lag? And based on our portal observation, 200 here. So they will identify based on the 200 observation, they will identify the maximum lag in order for the EViews to come up with the what we say the appropriate lag length, right? You cannot put too many. If I had 200 observation, I don't think EViews will put 200 lags, right? Or maybe 220 lag. So it will depend on the observation we put inside. So that's why you put a star here. Star means based on the maximum lag length. Then other than that I put default lah, because the bandwidth selection, right? Once you scroll down, they have N2s, they have a newlywed space, they have a newlywed. Normal one they will use default one, they will use newlywed. That means that this is the automatic, means that for bandwidth proposed by newlywed. Choose select the bandwidth selection. So this is something like adjustment in the test statistic, right? That normally we use the default one, right? Default one. Unless you want to come up with some justification, I want to use the Parsons one for this kernel. Why? You want to use the Parsons, right? So I use the default one, this one. Now I click OK. So this is my result.
How do you actually choose those spectral banding?
Default one, right, actually is already something like the what they use in the research, and that is particular something like the something like what we say more suitable one for you to do the analysis based on the proposed. That's why you can see, right, the published paper they will say, okay, for example this spectra, UV right, bandwidth based on the banner kernels. That's why we have to report in our table, okay, the bandwidth selection is based on UV best. That is something like what they use in the research. I use the research is based on the UV best approach. Because the another approach. You also use by other researchers, but we need some justification why you want to use. Maybe the puzzle that got found out that oh, Dewey West got some limitation. So because of the small sample, for example, like, they will use another version, to determine this band one. So that is the justification we have to justify that.
So it's not based on AIC or something, it's based on the limitations of the data.
This one is different. This one is bandmark is used to calculate the test statistic. What is the approach? Actually, what is the approach that used to calculate the test statistic? Is it based on Dewey West approach or based on the Puzzle approach or based on the fixed approach? So that is based on test statistic. For the model selection criteria, there is a use to select the net which use to account the overall correlation in the estimation. It's a different bit like this one. So that's that. So you can see the result here is one right? Yes. So filter reject, right? Yeah, because 4.20047 insignificant because the p-value now is 1. Very hard to get 1 also, but I get 1. So actually it's insignificant. So highly insignificant, so you filter reject. So what is the rationale? You filter reject means that my investment is not stationary at level. It's not stationary at level. How about first difference? Before we go to the first difference, you can see the individual result. You can see the individual result. What is the lag length for the individual firms, right? Maximum lag is 4. Yeah. Automatic lag is 0 to 3 lag. So automatic means that based on maximum lag. Maximum lag is 4. So they use the 0 to 3 lag. So for example, from number 4 they use 0 lag, and then from number 8 they use 3 lag, based on maximum 4 lag for each category, right? And then it's a bandmark also different across the firms. So these are the individual result, right? And also second stage coefficient. So the individual result, but what we concern is the general one. So based on ILC, 4.2 insignificant. So say it's not stationary at level. How about first difference? I go to e-views, I go to view again, I go to unit test, independence again, I first difference it. I want to see whether investment, once I first difference it, is it stationary or not? With the test equation, it's just an intercept. Then I can okay, so become negative 8.7, right? This is my result here. Look at right? So it's become negative 8.7. So you can see here, first difference, right? Yeah, is a D. First difference for the investment. For my 10 firm, again based on the maximum lag, range 0 to 3. Then based on maximum lag 3, then the result is significant. It's a p-value. Right? It's lesser than 0.05 if you based on alpha 0.05 here, right? So significant. So you reject. So it means that once you first differentiate, the series become stationary. So what I can say the investment is I1, right? Investment is I1. So this is just with the intercept, right? How about with the trend, right? So you can test, you can prepare a table and then test again whether the series stationary with the trend. But what we observed in the past, normally, they found that the series is stationary with the intercept. They will not proceed with the trend because already stationary with the intercept, right? So already stationary already, then people will not test with the trend. Or else if you just want to double confirm your result, you can test with the trend. With the trend also. So if you want to test with the trend, right, go to view again, just like what we did in the past. You just want to see level. Is it just now my level not stationary? How about the model with the intercept and trend? You click OK. Once you click OK, the result is 0.6, right? So again, it's not stationary at level with the trend models, right? So this is the model with the not only intersect, not only intuitive effect, also with the trend, right? This model intersect and trend. So again, the test statistic, you list all the series here, it's just a level. So again, it's less than 0.05. Sorry, greater than 0.05, right? So insignificant. So you feel to reject, right? Feel to reject. Feel to reject the rationale. Feel to reject the common unit root. So then you will motivate you, right? With the trend, right? With the trend, first difference. So I go again, go to view again, go to unit root test, and then test for the first difference. Stationary, right? Yeah, highly significant. So now, once I first difference, and then with the intersect and trend, again the test statistic here become lesser than 0.05. So now you reject already. You reject the rationale. So when combined with the previous result, you fail to reject in the level, then you reject in the first difference. So we can conclude that the investment actually I won. It means that you first difference the investment series, only the series become stationary. No matter the model with the trend or without trend. Right? This is our conclusion. So you can say investment is I1. So what it means by I1? Investment I1. Then you pray, right? You pray for hard, right? My CAP and BAL also I1. Then only no spurious regression. If your CAP and BAL are not, then there is an issue here already. You have a mixture I1, I0 series. You have a mixture I1, I0 series, you're going to have a spurious regression if you do not account for it. Because you combine because I1 means what? I1 means you cannot control, right? Because it's a non-stationary, the series is non-stationary. If you combine the non-stationary series with the stationary series in one equation, you will create the spurious regression. That's what we discussed in the time series, right? Spurious regression. So what you can do, if you have this kind of problem, I1, I0, then we have to use the panel ARDL. The ARDL we learn, do we learn ARDL in the problem, right? In the further, alright? I think so. I think we got learn the ARDL. We also have one called panel ARDL in a panel setting. That's what we call Pullman group. ARDL is proposed by Passara and 2001. We also have another version in a panel setting to account for the I1, I0 issue. That is called Pullman group. Then we're going to cover, I think, after our lab test, etc. Okay, let's take a break. Then we come back.